Hello everyone, today I'm going to introduce a tool for you. It's called the exchange buffers. It's a domain-specific language tool. We could use this tool to create the particles, binary particles definitions for different exchanges. Yeah, unlike the protocol buffer, it's a focus on the layout of the message itself. It's not focused on the API because when we writing the trading application with different exchanges, the most important part is the layout file of every message. We should make our data exactly the same as described in the spec. So in order to do so, I designed a type system of this language. Basically, I reviewed almost all the protocols I have worked on and summarized all the primitive tabs and the composite tabs, etc. And so now it could cover all the particles I have ever seen. But this part, especially the new composite tabs, we can implement more if we see more more data type in a new particle. So it has like a char, int, and unside int, fixed line string, float decimal. The float decimal I would like to describe a little because in the trading application we don't use a float number. We use the decimal number, but we would define a rule like maybe a number divided by 1 million. That's a real value. But when we send the value to the exchange, we will use the original value, but the real value of this field is this value divided by 1 million or like 1,000 according to the different data type. So in this way, the number will be accurate. Then the composite tabs, including enum, bfiles, and all kinds of message. The message is all those things, all those tabs actually eventually will be used in the message itself, and also several other statements like empty statement, insert an empty line in a particle, a comment. Comment will be translated to the C++ and the Python comment. So the CPP statement or directive, that's and the CPP and the Python, they will be translated to the different languages respectively. So that's just to give us a chance to write some any code, C++ code or Python code in our language, in the particle we are creating. So especially when we need some function which is not provided by the this tool directly, but we would like those parts can be in the final file, so we can use this way. So import primitive, we use this to introduce all those primitive tabs into the a language, because not all the protocol supports all of these types. Maybe some of them is not defined or not used in a particular protocol, so we have to use the import primitive instruction to import this primitive into the protocol, and then we can use it later in the message. And also when we do the import primitive, we can define the Indian information of the different types, and we also can define the max value, minimum value, or the null value for a particular type. So sometimes they have a special meaning in a particular protocol, but this raw primitive type doesn't have those information. We can control this by using the import primitive. And the include, this include is not like the C++ include. The include header file. So I'm talking about this, all those things under the DSL, this domain specific language scope. So this would include another language model to the current language. So the good example is the Millennium Protocol. Millennium Protocol, I implemented the LSE and the Turquoise, but they share the same session level message. So in this scenario, we can define the like a Millennium base as a base model can be used later by the LSE and the Turquoise. So that's include. So extern. Extern is it's just like a C++ extern or C++ extern. It tells the this protocol, this type exists but defined somewhere else. So typical usage is if we have some existing defined, like let's, for example, C++ class. That's a type. We define the type. We want to use it in this protocol, but we can't, or we don't want to define it with this domain specific language. We can just use this extern to import, not import, just extern to introduce this data type into the protocol. Then we can use it later. So so for the different protocol messages, we can divide them into two types. One is a fixed length protocol, one is a variable length protocol. For the fixed length protocol, any message of this protocol has a fixed length. So that means it has a fixed numbers of fields, the fixed length of fields. So the whole we would know this the length of a message when we know what is the type. So that's a fixed length protocol, like a Millennium Protocol, Aquarius Protocol, etc. Like this variable length protocol, that means the length of a product, the message can't be known in the beginning. So it might have some like a counter, let's say repeating group counter, indicates how many repeating group entries in one repeating group of the message. So one message could have many repeating groups. So the typical example is a T7 ETI protocol. Like we use the repeating group to define the different legs of the strategy instrument. And also this is a presence map. Oh, sorry, it's a presence map optional field. So there's a presence map. It's like a bit site. It has many bits. So one bit could decide if a field later after this present map will be present or not. So that means in the beginning we know the message type. Actually, we don't know how long of the message. But usually there's a field message length there. But for which field is in the message or not, we have to check this present map. Like when we read the message, or when we build the message for sending, we need to update this presence map, and also make sure the correct the payload will be appended to the message. So, and also there are two ways of creating the particle. I'll show you later. So first type is that we can manually create a particle like LSC turquoise, because there's no any exchange published layout file. So we have to read the manual and so create and then create equivalent data types or messages, and then finish the whole particle definition. The second type is for the T7 and Euronext, they publish some sort of layout file that describes the layout of all the messages. So I have implemented something in the tool to pass this file and create the AST tree directly. Then so for such kind of the particle is much easier. Each time when the exchange releases a new version of the particle, we just need to use those files to rebuild the particle and then generate the CPUPAS and the Python code accordingly. So here are some particles already implemented. LME new trading platform. So that will be go live 2023 May. So T7 11. So that's like November of 2022. So SPE protocol is been there for a very long time, and just keep releasing the different versions like T7. This is a T7 Euronext, but this LME new trading platform is fresh new. Previously we are using the LME Select number 1, number 2, but now they have a fresh new trading platform. And LSC turquoise. So for those two particles, it's been a while, so I think I need to cross-check the new spec and correct or update some of the fields. So there's no issue. I will explain it later. And then here's a tool. I implemented a tool for it's called debug terminal. So I use this tool to test the generated CPUPAS and Python files. So for me, usually I write the Python test case. Test case is to test a C++ application. So a C++ application in this scenario is we call it a router. The router, the functionality of router is simple. It's just it receives a message from upstream. So that's a fixed message. So in our test tool, we have a fixed client to send a fixed message to router, and then the router would translate the fixed message to the binary protocol message and send to the simulator. So the simulator, for simulator, we generate the Python code and C++ code. The simulator would use the generated Python messages to decode the message sent by the router and the response accordingly. So the router itself used the C++ protocol layout file to do the conversion. So yeah, and all the messages will be put in a queue, the message queue. So in the code, I think it's called historical queue. So this then all the messages can be displayed by a web-based viewer, message viewer. It's implemented by with the dash. Okay, that's all for the brief introduction of this project, and then so let's let me give you some. Let me try it.